Okay, moving on to 5.2. We're going to continue with our exponential functions. So in 5.1, we looked at the graph of y equals 2 to the x already. Graphs in the form of y equals b to the x, where our bases were greater than 1. So our red graph here is our graph of y equals 2 to the x. And we know that if x were 2, 2 squared is 4. If x were 1, we'd get the point 1 comma 2. If x were 0, 0, 1. If x was a negative 1, we'd get 1/2. A negative 2, we'd get 1/4. So our graph of y equals 2 to the x is just that red graph that is shown there. If we were to sketch the graph of y equals 3 to the x, which is our graph in green, we know that if x were 2, 3 squared would be 9, which would be way up there. If x was 1, 3 to the first power is 3. If x was 0, 3 to the 0 is 1. If x were a negative 1, we would get 1/3. If x was a negative 2, then we would get 1/9. And our y equals 3 to the x would be that green graph. So if we were to sketch y equals 2.7 to the x, well, if the red graph was 2 to the x and the green graph was 3 to the x, then it should make sense that 2.7 to the x would be somewhere between those, a little bit closer to our 3 to the x versus our 2 to the x, which is that blue line, that blue curve that we see in the picture there. So y equals e to the x. E is just a number. It's a very, very important number. You will work with it a lot in calculus, but you can think of it like pi, where pi is it's an irrational number, a non-terminating, does not repeat, can't write it as a fraction number, where e is approximately this 2.71828. It is referred to as Euler's number. One way to remember it is, for you history gentlemen out there, Andrew Jackson. He was in office twice. He was our 7th president, and he was elected in 1828, which coincidentally are the first 6 numbers in Euler's number, this number of E. There are a number of different ways that we can calculate E that in calculus you would look at, where we can look at a form of compound interest, we can look at summations, but for our sake for this year presently, we just want to know that E is just this constant. It's this number, approximately 2.71. So we're going to just treat it just like we would treat pi. Just another number that we're going to be working with. Okay? So let's go and we look at some graphs here. We have y equals e to the x, which is approximately y equals 2.7 to the x. And our graph of y equals 2.7 to the x, well, we know is just going to be increasing from left to right, where as x is getting larger, our graph is getting larger in quadrant 1. As x is getting smaller, our graph is getting closer and closer to the x-axis in quadrant 2. And if x were 0, e to the 0, we have this y-intercept of 1. We have a horizontal asymptote at y equal to 0. Our graph is getting closer and closer to the x-axis, that line of y equal to 0, as x is going towards a negative infinity. If we were to sketch the graph of y equals e, 2.7 approximately, to the x minus 1, Well, we know that's just our basic graph in number 1, where that -1 is just telling us to take that graph and shift it to the right 1 unit. So if we take what we just did in number 1 and we shift everything over 1 to the right, basically we're still looking at a very similar graph where it is increasing from quadrant 2 into quadrant 1, where our domain would still be everything. We could plug anything in. Our range is still above 0. Our x-intercept is not going to exist. Our graph is not going to touch that x-axis. Our y-intercept, if we replace x with 0, we're going to just get e to the -1, or 1 over 2.7. I'm just going to put it as 1 over e. And we still have that horizontal asymptote at y equal to 0. Our graph is still approaching that x-axis, that horizontal line of y equal to 0, as x is going towards a negative infinity. On number 3, we're still looking at that basic graph in number 1 of y equals e to the x. We just know that the negative out in front of the function has told us to flip that graph over the x-axis, and that -1, as we just saw in number 2, tells us to shift that graph to the right. And so if we take what we've done, we always move left or right. We take our graph, which we just did in number 2, shift to the right, and we flip that over the x-axis. Now our graph is going to be down here in quadrants 3 and 4, decreasing from quadrant 3 into quadrant 4. Our domain now has shifted from a negative infinity up to 0. Oh, take that back. I lied. Our domain, sorry, half asleep here. Our domain is still everything, negative infinity to infinity. Our range is the negative infinity up to 0. We know our graph is still not hitting the x-axis. They do not exist. Our y-intercepts, if we replace x with 0, then we're going to get minus e to the -1, or -1 over e. So approximately a -1/3. And we still have our horizontal asymptote at y equal to 0, as x is going towards a negative infinity. And our last graph here is the same graph we just did on number 3. The only new addition is we're shifting everything up 1 unit. So if we take what we just did on number 3, where we have shifted to the right, we have flipped it over the x-axis, and now if we move everything up 1 unit, because we know we always go up or down last, then our graph is still looking something along the lines of that, where it is decreasing. And our now domain is still our negative infinity to infinity, but our range now has shifted from a negative infinity up to that +1. Because keep in mind, if we had a horizontal asymptote here at y equal to 0 and everything has shifted up 1, then now our horizontal asymptote has moved up to y equal to 1, which means our range values now go from a negative infinity up to 1, not including that 1. We now do have an x-intercept. I'm actually going to come up here. X-intercepts, we know that we set y equal to 0. And if I set y equal to 0, I'm going to have 0 is equal to minus e to the x minus 1 plus 1. So bringing my e term to the left, And I know that in order to solve, if the left side is equal to the right side, I want to have like bases if I can. And I can rewrite that with a like basis because I know 1 is the same thing as e to the 0 power. And so now if my bases are the same, that means that my exponents would have to be equivalent, and I get an x-intercept at 1. So my graph is intersecting here at 1, 0. My y-intercept, well, y-intercepts, we always replace x with 0, and if I replace x with 0, I'm going to get minus e to the negative 1 plus 1, or that is a negative 1 over e plus 1, so approximately a negative 1/3 plus 1 is right around approximately 2/3 for our y-intercept up here. Okay. So we're doing the same things that we've always been doing as we were shifting and translating graphs. We were just basing it on our basic graph of that e to the x, which was very similar to what we just did in 5.1 of that basic graph of y equals b to the x, or how we were working with the 2 to the x. Okay, so just to get a little more comfortable with this e number, this constant, this number that's approximately 2.7. True or false here? Is e less than 1/2? So is approximately 2.7 smaller than 0.5? We know that that is definitely false. Okay. Is the square root of e less than 1? Is the square root of approximately 2.7 smaller than 1? Well, we know that the square root of 1 is 1, and you have a number larger than 1, so that is definitely not going to be smaller than 1. So that would be false. On 3, e squared, is e squared smaller than 9? Well, again, e is approximately 2.7. So is 2.7 squared smaller than 9? Well, we know 9 is 3 squared, and 2.7 is smaller than 3. So that quantity definitely would have to be smaller, the e squared. On 4, e to the negative 1, is that smaller than 0? Well, again, e is approximately 2.7. So is 1 over e, or 1 over 2.7, smaller than 0? No, it's just a fraction. It's not negative. It's just a number, 1 divided by 2.7, or approximately 1/3. On 5, is e smaller than 5/2? Is 2.7 smaller, approximately 2.7, smaller than 2.5? No, false. Okay. On 6, e squared, or 2.7 squared. Is that smaller than 4? And we know 4 is just 2 squared. Well, obviously 2.7 is larger than 2, so that is going to be false. E cubed, or 2.7 approximately cubed. Is that smaller than 27, or 3 cubed? Well, 2.7 is smaller than 3, so yes, that would have to be true. And lastly, on 8, e to the 0 equal to 1, or approximately 2.7 to the 0. Well, anything raised to 0 we know is equal to 1, so yes, that is true. So anytime you see e, again, it's just a number. You're just working with this approximate value of 2.7. Okay? And last one, looking at number 2 here. N of t is this e to the t power, this exponential, where our base is this number greater than 1. Our base is just 2.7. And N of t represents the number of bacteria, and t is representing our hours. And we want to find our average rate of change. Remember, average rate of change is just a way of expressing slope in our function notation over the interval from 5 to 7. And recall, if you are just calculating a slope, that interval is always the x's of our 2 points that we are calculating that slope, that average rate of change. And we take those x's and we plug those x's in to our equation to get those corresponding y values. So if I have 5 and I plug that into my n of t, I'm going to get e to the 5. And if I take my 7 and I plug that into n of t, or n of 7, I'm going to get e to the 7. So if I go and I calculate my slope, e to the 7th minus e to the 5th over 7 minus 5, change in y over change in x, and I just get my e to the 7 over minus e to the 5, all divided by 2, which if you were to plug that into a calculator, you would get approximately 474. Okay. So again, E, when you see E, it's just a number. It's approximately 2.7. Just any other constant number that you would work with, you are just going to use the letter E to represent that number. And that is it for 5.